Hello, this is Brandon McCullum. In this video, I will be discussing the material balance for isopropanol synthesis. So we have our main reaction here, right? We react propylene with water, and that gives us our, well, not our isopropanol, right? So C3H6OH. And then this isopropanol can react with itself. So 2-isopropanol produce a diisopropyl ether. So 2C3H6O plus water. Okay. So these are our two reactions that will occur. If we look at our components here, we have propylene, ether, alcohol, and water. And right, so these are our four components, and we have our reaction. Right, so we have some reactor and an input of propylene and water, and outputs of our ether and our alcohol. So we can say this propylene will have will be a mixture of all four of these. In this case, we want pure propylene, so I will use 1000, and we also want pure water, so 0001. Right? And each number in here corresponds to the number in the list. So the first mole fraction is for propylene, the second is for ether, and so on. And we can also say we have a flow, or we can also measure the flow rate of our water and propylene. And then we also have, if we look at more variables, we have the extent of the reaction 1, the extent of reaction 2, right? And then we have the ether with some mixture here, and the alcohol is some mixture, and with some flow rate. Now what we want to do is we want to make sure we have the same number of unknowns as equations. So if we look at how many components we have 4 components, right? And each of these components has an equation where we have some flow going in, we have an extent for the reaction, and some flow going out, right? And we want a net zero, right? So the flow in minus or plus whatever is removed or added during the reaction must equal the flow going out, right? So that means we have 4 equations, which means we have 4 unknowns. So we can also, so if we look here, we have 6 right now. So we must specify 2 more. We're going to say this ether has an output of 0.001 propylene, 0.9 ether, 0.09 alcohol, and 0.009 water. Right, so that's one more variable, and then we can also do the same thing for alcohol. We can measure the output here, so 0.001, and then very little ether would be 0.01, and then it's mainly alcohol, so 0.94, and then 0.49, right? So we measure our output, it gives something like this. And based off of that information, like I said, we have 4 equations here. Now we have 4 unknowns, right? The extent of each reaction and the flow rate coming out. And we can now create a system of equations to calculate our unknowns, which I will be doing in code. Here I am in Colab. So right now I have this imported here. Right. So the main thing I will be using is this dictionary and this D2NT that will convert the dictionary to a named tuple. Right. So the first thing I want to do is import numpy np and from scipy.optimize import my my root solver. Right. And then I'm going to go ahead and create a dictionary. Right. So e equals .dict with parentheses there. And now I'm going to go ahead and write in my variables. But instead of, so for instance, right, I have my propylene feed equals 100 moles per second. To put this in the dictionary, I need to write E dot in front. So I'm going to do that for every variable here. So E dot propylene mole fractions, and we have np dot array 1 0 0 0, and we have our water feed equals 95 moles per second, and our water mole fractions, we have another array that is 0 0 0 1. All right, and then I also have my products. So E dot ether feed, or not ether feed, ether product. We don't actually know the flow rate. So for this, because we are using a dictionary, because we have bounds, we want to use this range here. Right, so we give it a guess, we'll say 5, and then the absolute lowest it can go is 0. And then I'm going to add a little bit here. Right, so we want to figure out what our maximum value is going to be. So if we write out reaction 1, we have C3H6 plus H2O goes to our isopropanol, so C3H7OH, and then we have reaction 2, right, and that's 2 isopropanol goes to our ether, plus water. So looking at this, we see for every 1 propylene, we get half an ether. So this maximum value will be our propylene feed over 2. Now, the reason we aren't taking water into account is if you see here, right, we add water in the beginning, but then the reaction also produces water, right? And along with that, if we look at our diagram here, right, there's a water recycle, so we have the water flow going in to the triple bed reactor plus the water recycle going into the triple bed reactor. So the reaction is actually dependent on the amount of propylene of our alkene up here, right? And not on water. So we want to use our propylene feed. Then we have our ether molar composition, and that is going to be an array. We have, I'm just going to copy this, and then we have our alcohol product, right? And that's going to be the same idea as the ether. This one we're going to guess is a little higher. It's got a low of 0. And then this time, right, 1 propylene creates 1 alcohol, so the maximum is going to be our entire propylene feed. And then our alcohol molar fraction, or mole fractions, I'm going to again copy and paste that with parentheses and brackets. All right. So now I need to do the extent of the reaction, right? So the first thing I actually need to do is write out our stoichiometric ratios here. So the stoichiometric ratio for reaction 1 is going to be an array. And if we look here, right, reaction 1, we lose a propylene and a water, and we gain an alcohol. So we're going to do -1, 0, 1, -1. And then for our stoichiometric ratio for reaction 2, we have an array, and that is going to be no propylene plus 1 ether minus 2 alcohol and plus 1 water. And then we can go, and then we can write variables for our extent of reaction 1, right? And that's going to be a range because that is one of our unknowns. And we can make a guess. We'll just say it's going to be the propylene feed over 2. Its minimum is 0, and its maximum is the propylene feed. And then our reaction 2, this one, we actually need 2 propylene for each ether. So I'm going to use the same values in my range except halved. So our initial guess will be propylene feed over 4, and then our maximum is our propylene feed over 2. So now I have all of my variables here, right? We have our 4 unknowns, and so now we need to write in our 4 equations. So if we define a function here, define equations given a dictionary, right? We say feed equals d dot propylene feed times d dot propylene y. Oh, I missed the period. Plus our d dot water feed times d dot water x. Our reactions, we have E dot stoic reaction 1 times E dot extent of reaction 1 plus, D here, right? Because that is the letter we used up here. Right. So now we do the same for reaction 2, and then our product is going to be equal to d dot ether product times d dot ether x plus d dot alcohol product times d dot alcohol x. And then we want to return our feed plus our reactions, right? We add our reactions because here, anytime we subtracted or anytime something was used, we used a negative. Anytime we produced it, we used a positive. And then we want to subtract our products. All right. So the reason that we use a dictionary here is because without it, we would enter some vector, right? So for instance, we'd have V, and then we'd have, the extent of reaction 1, extent of reaction 2, so on, equal to V. but that means that anytime our unknown changes, we would also have to change the function here, right? So if we use a dictionary, that's no longer a problem. We would just change the values in the dictionary. Okay, so now if we want to use our root solver, right, it doesn't work on this this function here because of the dictionary. It will sort through all possible values and not just within our range. So what we need to do is first use this d2nt function, right? So that's a dictionary to named tuple for our E dictionary, and we want to unpack that. So we have x naught, that's our initial guesses, or x to nt, our x to unknown, and our constants. So this will unpack all of our values here for our ranges, and then our constants are like our ether x, our known variables, right? And so we unpack that. I need the wrap function in here. All right. So now with this wrap, right, we can say our wrapped equations equals wrap of equation. Right. So this is what we will use for our root solver. Then we do root of wrapped equations in our x naught initial variable dot x. I need to add a p here. And I need to do ether x. All right, so I found my error here. This alcohol mole fraction should be np.array, and this 0.49, it just pasted wrong. It should be 0.049. All right. So now this function works, and we can list our constants as a dictionary. All right, so there they are. And then we can also, if we take x to unknown, for x, we can paste all of our unknown values as a dictionary, and we have our ether product stream, alcohol product stream, and the extent of our two reactions. And that will be all. Thank you.